Hello, we're going to start with section 5.2, gas pressure. Gas pressure or temperature and kinetic energy both have a whole lot to do with gas pressure. So the temperature, as we've already studied when we studied about different phases or states of matter, the temperature determines how far apart those atoms are, whether they're in the solid, the liquid, or the gaseous state. And then the warmer those gas molecules are, the more kinetic energy they have. So the formula for kinetic energy is 1/2 times the mass of the gas molecules times the velocity squared, how fast those molecules are moving. Now, together, those things impact how much pressure the gas produces. So, very interestingly, any two gases at the same temperature have the same average kinetic energy. Now, it doesn't matter if the molecules are really tiny, such as helium gas, or if it's a polyatomic molecule of gas like this refrigerant. Um, they they have, if you look at this equation over here, it's 1/2 times the mass. So helium, of course, would be a lot smaller, less mass than the freon over here. But the velocity, the helium gas molecules can move a lot faster. So to compensate and make up to have the same kinetic energy. So if we envision Speedy Gonzales here or a sloth, one of them is a lot smaller and one of them's bigger, but Speedy Gonzales is going to be a lot faster and the sloth will be slower. But if you multiply all the parts, it could have the same kinetic energy. So just to underline how fast they were. Now, if we think of how you inflate a balloon, so it's full of all these gas molecules. We blow in the air, and what makes that balloon have its shape is those molecules hitting the sides of the balloon. Um, so the sum of the forces of all the molecular collisions with the total area of the container walls results in the gas pressure. So the temperature and the kinetic energy makes them move around really fast, and them moving around really fast makes that have pressure. So pressure, a noun, is a force per unit area due to the collisions of gas molecules against the container walls. The formula is pressure equals force divided by area. Now, so it requires three things: these molecules to be in the gaseous state, and they're moving around with their kinetic energy, and they're striking the walls of the container. So even this tea kettle, you can imagine there's water in here and it's boiling, so it's changing state into a gaseous molecules. And as it's boiling, the higher the pressure of all those gas molecules in there are, until it gets so crowded in there that it starts looking for the path of least resistance, and the gas can escape through the spout, and it goes through the whistle and makes its escape. So what is standard pressure? So if you think about the pressure of the whole atmosphere, all the way from the top down to the bottom, to the land, we have that pressure weighing down on us. So where would you measure standard pressure? We have places all over the world, that you could measure the pressure at, but where is standard pressure? So standard pressure is found at sea level. So the at the bottom right here on the ground at sea level, how much pressure that column of air is. So, of course, as you go up a mountain or at higher elevations, there's less air pressure on you. So that is where you would have the most air pressure in the world. So all of these different units are ways to measure air pressure. And right here, they're all equal to what the pressure is at standard pressure. So in chemistry, the most common thing that we're going to be talking about is the unit of atmospheres. So if you even think about it, the weight of the whole atmosphere, one column of air, one atmosphere deep, is how is the unit that we most will be using. Now, alternatively, 760 millimeters of mercury or 760 torr are also common. So we'll be talking about that even today, but in chemistry, we'll be using that a lot. Now, the fourth unit over here, 101.325 kilopascals, that's also a unit of pressure, and that's the SI unit of pressure. It's used in physics and engineering, and well, actually, the SI unit of pressure is the Pascal. And 1 Pascal is defined as 1 Newton of force per square meter. And your book says that 1 Pascal is actually a very, very small amount of pressure. It's approximately equal to the pressure of a 6-gram sheet of typing paper, how much pressure that exerts on the surface underneath it due to its weight. So you think about a sheet of paper, it does not exert a lot of pressure. So that's why we use kilopascals, because it just wouldn't be much of a measurement. Now, the bars and M bars are mainly used by meteorologists. And then the 14 or the pound PSI, the pounds per square inch, we're familiar with that for our bicycles and car tires and basketballs and things like that. The unit torr sounds a little weird. It was named in honor of the inventor of the barometer, Evangelista Torricelli. So he invented that in 1643. And what he did was he had a glass tube that had a closed end, and he filled it full of mercury. And then he turned it upside down in a pan of mercury and noticed, so it created a vacuum up here at the top of the column. And he was the first to figure out that that was the pressure of the atmosphere pressing down on the mercury level in the pan of mercury, and it was pushing it up into the glass column. So standard um, atmospheric pressure is 760 millimeters of mercury or 760 torr. So as long as he had this column that was taller than 760 millimeters, which is about 29.9 inches. So as long as that tube was taller than that, it would have some space up here. Now, the third picture is Blaise Pascal, and Evangelista Torricelli did not live very long at all. He died when he was 39 years old, and he died just a few years after he invented this. And I'm not sure that he published it a whole lot, but Blaise Pascal really took off with it. And he found that as he carried that up a mountain, as the pressure decreased, that column of mercury would go down, and drop as he was walking up the mountain. And he did a whole lot of studies and things before. So that's why we have torrs and Pascals, because Evangelista Torricelli and Blaise Pascal. And remember that it's a good idea to remember and memorize these 4 units up here, because in the future chapters, we're going to be converting back and forth between these 4 measurements. So some ways to measure pressure. So some of these are really familiar, like here's a tire. Um, I never noticed that it had the kilopascal measurement on there. I just paid attention to the PSI. So anyhow, it is on there. They circled it in red, 300 kilopascals or 44 PSIs. Then here is a barometer. Now, barometer is the name that, let me go back just a second. Yeah, so Evangelista Torricelli, one thing that he said, we live submerged at the bottom of an ocean of air. So the Greek word for barometer is, or the Greek root word, baro is means weight, and meter, of course, means measure. So it means measuring weight. And that just seemed kind of odd, to name something that measured pressure, air pressure, to be something that measured weight. But he made that statement that we live at the bottom of an ocean of air. And he was convinced that back then people thought that air didn't weigh anything, and he was trying to show that it did, and that we have this invisible weight on top of us. So I think that's why it's called a barometer. I'm not sure about that, but I think that's why. So now we talked about how normal air pressure is 760 millimeters of mercury. This barometer, it doesn't have millimeters of mercury. It's got millibars on the inside and inches on the outside. So here's 29 inches, there's 30 inches, and 31 inches. Now, 760 millimeters of mercury is equal to 29.9 inches. So there's 29, and right here is 0.9. So it looks like it's just a little bit less than that. And then the copy didn't, it's a little too pixelated to read, but these inner numbers right here, this is 1,000, that's 1,010 millibar, there's 1,020 millibar, 1,030 millibar. So anyway, this one shows a little bit over 1,010. So 1,013 millibar is normal, is equal to 760 millimeters of mercury. So this kind of barometer is used to measure or predict weather, and used by meteorologists to know when a front's coming through or when one's leaving, or so forth. Now, the third kind of pressure measurer is a blood pressure cuff. So it kind of seems weird now to see 120 over here on this meter, 120 millimeters of mercury. So we know that 760 millimeters of mercury is normal air pressure. So you'd think in our bodies, that it would be more. But the thing is this kind of meter does not account for outside pressure. So this is the pressure that our heart is pumping. In addition, we would have to add this on to 760 millimeters of mercury. So it's 120 plus 760 would be the actual pressure of our blood. So our bodies can withstand the pressure of the atmosphere down on our bodies, and it's still pumping blood in addition to that. So our blood pressure is not truly less than the outside air pressure. Okay, so how does an aneroid barometer work? So this is the middle picture that we just looked at that it's one of the types that a meteorologist would use. If you looked at it on the inside, it's got these little metal coils and springs and levers and this sealed box right here. So let's watch this one little video clip. It's 65 seconds. It's really short, to show how how aneroid barometers work.
Aneroid barometer. Its construction includes a thin sealed metal chamber having partial vacuum inside. This chamber is fitted with certain levers and spring mechanism to which a needle is connected. A graduated circular card shows the barometer readings in millibars or hectopascals. The whole assembly is enclosed in a metal casing. The thin metal chamber has elastic properties. When atmospheric pressure increases, this chamber gets compressed. When atmospheric pressure decreases, the chamber gets expanded. This inward and outward movement of the chamber acts on the needle mechanically, and the needle then registers a reading on the graduated card. The accuracy of the reading depends upon the size of the metal chamber. If the chamber is large, accuracy will be better.
So I thought that was a better explanation than me trying to say that, but it's really cool how the pressure on that disc can make those springs and things all turn the needle on the dial. So one other kind of um, thing used to measure pressure is a manometer. And we're going to study about two different kinds of manometers, the open end manometer and the closed end manometer. So an open end manometer has one arm that's open to the atmospheric pressure. So the right hand side in all these pictures. The other arm is attached to a gas sample, and mercury is in the tubing in the middle. So in our first example here, our gas sample is exerting pressure and the atmosphere is exerting pressure. So as long as the levels are exactly even, then there's no net change of pressure. And so they're equal. So that the pressure that the atmosphere is pressing, it shows us here at 760 torr. And so the pressure that the gas is pushing is equal. So also 760 torr. So both of these are 760 torr. Now in the second example, the atmosphere is pressing down, so there's 760 torr, and then we have a mysterious gas here, and it's pressing down as well. Now, this you can kind of think of as kind of like an arm wrestling situation. So the atmosphere is pressing at 760 torr, and then the gas sample is pressing its pressure. So look at the heights of the two sides and which one is winning. So it would be the sample gas over here. It has pushed a lot harder than the air pressure out here, and it's had to retreat, you know. So we take this difference. So it looks like 550 right here, 550 torr, and right here is around 100 torr. So 550 minus 100 is around 450 millimeters of mercury, or 450 torr. So since the sample gas is winning, we need to add this amount to the air pressure outside. So 760 torr plus 450 millimeters is 1,210 torr. Now let's look at the opposite example here. So the third one has The atmosphere is still 760 torr. Now, always check this because it can change. There's a lot of variation from day to day what the atmosphere is. But in all three of these, it's 760 torr. So the atmosphere is pressing down, and we've got the gas sample and it's pressing down. But the outside air pressure is winning. So we know that this one is less than 760 torr. So we need to subtract this difference. So there's a difference of 550 millimeters of mercury. And 760 torr minus 550 is 210 millimeters mercury, or 210 torr. So this sample of gas is only its pressure is 210 torr. All right, so the second type of manometer is the closed end manometer. One arm of the U-tube is sealed in a vacuum while the other arm is still attached to the gas sample and the mercury is in between. So unlike the open-end manometer, the atmospheric pressure has no effect on these measurements. We just subtract the difference between the two ends of the mercury, and that is the measurement of the pressure of this gas. So it looks like this one's 550 and this one's 100. So 550 minus 100 is 450 millimeters. So there you have it. It's 450 millimeters mercury, or 450 torr. So the closed-end manometers are really easy to calculate how much pressure the gas has. So let's practice. Okay, so this one is an open-ended manometer. What is the pressure of the neon gas sample in this manometer shown on the right? Hint, convert to millimeters of mercury. So it shows us 5 centimeters. So do you remember how many millimeters are in a centimeter? So there should be 10 millimeters in a centimeter, so that would be 50 millimeters. The air pressure outside is 748 millimeters of mercury. So we've got the outside air pressure pressing down, and we've got the gas sample that's pressing down also. And which one is winning? So the outside air pressure is winning, and the neon gas is less. So we need to subtract 700, take 748 and subtract 50 millimeters of mercury. So 748 millimeters of mercury minus 50 millimeters of mercury is 698 millimeters of mercury. So we could say 698 millimeters of mercury or 698 torr. Either one. Number 2. So this one doesn't have a picture. It just describes the problem. What is the pressure of a gas sample in an open-ended manometer if the mercury level on the atmosphere side is 30 millimeters higher than the level on the flask side? The air pressure is 753 torr. So we've got the air pressure is 753 torr, and then the mercury is higher on this right-hand side than it is on the left-hand side. So if it's higher on the right-hand side, which side is winning? Is it the atmosphere side or the sample of gas side? It would be the sample gas side. Okay, so it would be and in order for it to defeat or win over the atmosphere, it has to be more than this. So we have to add. So we have 753 torr, and we're adding 30 millimeters of mercury. So here I just drew a little sketch of the open-ended manometer here. The gas sample 1, right? So 753 millimeters of mercury plus the 30 millimeters of mercury. So the total pressure of the gas sample is 783 millimeters of mercury, or 783 torr. Now, the last question to practice with in the sample is to practice with a question about the closed end manometer. So what would be the pressure of a gas sample in a closed-end manometer if the difference in heights of the two mercury levels is 345 millimeters? So remember, this one, it does not take into account the atmospheric pressure. And your book especially likes to try to kind of make you second guess yourself, and it tells what the atmospheric pressure is just to throw you off. So if it says in a closed-ended manometer is blah, 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 and the outside air pressure is 760 torr. So you just have to ignore the extra information. Now here it doesn't have any extra information, but when it says that the difference of the heights is 345 millimeters, then that is the answer of the pressure. So the difference between here and here is 345 millimeters, and that means that the answer is 345 millimeters of mercury, or 345 torr. The closed-ended manometers problems are just really easy to do. So that brings us to the end of section 2. Section 3 is going to be a long one, but we'll get to that one next week. Bye. See you Friday.